Calculus BC, we're moving to 6.4, and we're really dealing with a physics type of a problem. But furthermore, I want to let you all know that this is a BC only topic. What I'm getting at is simply this. If you have friends who are in AB calculus, they won't study these types of problems right here. And most typically, if you would get a problem like this, it's generally going to be on the multiple choice. But let's take a look at this learning target. I can find work stretching a spring here. And if you've done this in physics, calculating work, as you can see up in this top left corner, is very simply a measurement of force times distance. In customary units, it will be in foot-pounds or in inch-pounds. In the metric system, we would calculate work to be in Newton meters. But a Newton meter is also referred to more simply as a joule. Joules. Well, here's the next little aspect. The force, as you are using that on an object, very often is not constant. If you've ever found that a car has stalled and stopped, you're going to know what I'm talking about. If you were asked to help push that car, at first you'll be exerting a tremendous amount of force to try to get that car moving. But once it is moving, you won't have to exert nearly as much force. We're going to see with a spring, it's very much the same way. If you're stretching or compressing a spring just a little bit, you won't have to be using quite as much force. But as you really try to begin to stretch that spring further and further, it's going to take more and more force to do that. What that means is that could be rather complicated to calculate work. So let's suppose that the force moves an object along the x-axis from x equals a to x equals b. Let's also assume that the force at any one moment could be different at one position compared to another. Now, because force is going to get multiplied to distance, you're going to see that at any particular moment in this problem, you're only going to be using that force for a very small distance, and we're going to use delta x to represent that. Look here in the middle, you can see that we would have this little increment of work, a tiny sliver of distance. And what we could do is find the force like at a z sub k perhaps at this moment. And this is where this next asterisk is going to be coming into play. This is a little increment of work. You can say there's some force that is being applied at a particular distance here at z sub k. But if we were to multiply that over a very tiny little distance, then we'd be able to calculate the work done on this distance of delta x sub k. Well, imagine that we just kept doing that. We sliced this problem up into very, very tiny delta x's, and we'd calculate all these work increments, delta w's. If we add that up, you're probably going to say, now wait a minute, that sounds so much like what we were doing with Riemann sums. And indeed it is. It's an integral. So look here in green, what you're going to see is f of x is the force applied at a particular x value. dx is this infinitesimally small little slice of distance. And you multiply that together, and that's a work increment. But we're going to calculate that like a infinite number of little slices from x equals a to x equals b. And then we're going to be able to calculate work. So Hooke's law, you can see right here, Hooke's law is definitely something that comes into play a lot in physics. We've also used it in math before too. The force, f of x, required to stretch, or please add this, or compress a spring. So we can either stretch it out or push it in, compressing it, X units beyond its natural length is given by f of x is equal to some constant k times x. And we're going to have to find that f of x. And you can see why in this integral up above where I'm putting the stars around here. That's what's going to go inside of our integral. So let's just begin reading example 1. It says a force of 10 pounds is required to stretch a spring from its natural length of 8 inches to a length of 10 inches. So here's what we're going to have. We've got this spring, okay? And, we've got this spring right here, and this is, tell you what, I'm going to actually draw this over to the side here just for extra space. This is 8 inches. By the way, we could call this ground 0, so to speak. This is a nice way to do this. This is 0 units beyond its natural length. But if we're going to stretch that to 10 inches, well, I'm going to change my color here just to show that change. 10 inches would be over here to the right. Well, what position would we be at? We'd be 2 inches to the right. This would be x equals 2. Okay, so this is 2 units beyond its natural length. Why is that so important? Well, we need to know what x is. So let's go ahead and get to work with Hooke's law. We'll say f of x is equal to k times x, okay? And we're going to find the work done in stretching the spring from its natural length to 9 inches, actually. But look, it took 10 pounds of force. So I'm going to write 10 right in here. And we're moving that 2 units beyond its natural length. So when I divide by 2, I'm going to get k is equal to 5. Very importantly, that means f of x is equal to 5 times x. We're not done with this problem, but now we have a force equation for a spring. If we wanted to move 3 inches beyond its natural length, 4 inches, whatever that is, simply plug that in for x, and then you can calculate how many pounds of force are needed to do that. Well, for part A here, it says find the work done in stretching the spring from its natural length to 9 inches. Well, let's see here. We know that 8 inches is its natural length. We called that x equals 0. And we're going to go to 9 inches, so we're going to go just a little bit further to the right. Right over here. And that would be x equals 1. We're 1 step to the right, 1 unit to the right of its natural length. Well, we're trying to calculate the work done going from here at 8 inches, ending at 9 inches. So if we were to look up at this green highlighted formula, we're going to say, well, the work is integrating from A to B. Well, we're at 0 inches from our natural length, going up to 1 inch from our natural length. And inside we have f of x times dx. By the way, you always want to have bounds communicating how many inches you are from your natural length. Why? Because Hooke's law is written that way. Hooke's law is actually written that way. So, look, it's silly to even try to use an FN int here. Look, we're going to bump our power up 1 step by 2, divide by 2, and very quickly finish with the fundamental theorem. When we plug in a 1, we just have 5 halves minus 0. Well, what units do we have? It's inch pounds. Inch pounds. So 5 over 2 inch pounds of work. Let's just say that you were given instead, for part B, by the way, it's our last problem here, amazingly, you're going to find the work in compressing the spring. So let's very quickly just bring this back up and say, hey, we've got 8 inches for a natural length. But now what? We're going to say, wait just a second. We're pushing it in. And I'm exaggerating a little bit. We'll say, here's your 7 inches. Well, what's going on here? We can say, well, this is ground zero. This is 0 units from our natural length. X equals -1. You can certainly let X be negative to communicate that you are compressing it. It's almost like we've got a number line here saying, look, this is showing the difference between stretching the spring out 1 inch and pushing it in 1 inch. Now you might wonder if that's going to be a different measurement of work. By the way, we've still got the same spring, so we've got f of x is equal to 5x. So how do we work this out? Pun intended. Work, we're going to say start at 0, right? This is where we're starting. Go to -1. Wow, look at that. What's f of x inside? Well, it's, with Hooke's law, 5x, and here's your dx. Lots of times kids will say, well, gosh, should you flip the bounds? I want to point something out. You don't have to. Look, we can bump this up to a 2 and very quickly plug in our -1 and our 0. Hey, when you plug -1 in, you're going to immediately see, I hope, that you're going to get the exact same thing that you just had before. Wow, look at this. It's the exact same amount of work to compress the spring 1 inch from its natural position, as well as stretching it 1 inch. So just wanted to show this to you. One of the shortest lessons of the year. We are done.